Hello, my name's Steve Lofts and I'm from the Centre for Ecology and Hydrology in the United Kingdom. I'm going to give a short presentation on the Biotic Ligand model, which is a tool for explaining how water chemistry affects the toxicity of metallic contaminants, which can include metallic radionuclides. It's been known for several decades that water chemistry exerts important effects on the toxicity of metals to aquatic organisms. And the BLM is a tool to help explain why this happens and also to help incorporate this into risk assessments. So this chart explains the issue. What it shows is the toxicity of copper to the water flea, Daphnia magna, across a series of different water chemistries. And the higher the bar, the less toxic is the copper in that particular water. And we can see that across all these waters, there's a considerable variation in the toxicity of the copper by over an order of magnitude. Now, data like these are a challenge for risk assessment because if we can't explain why this variability occurs, then we're faced with the prospect of setting safe concentrations of metals in waters that are towards the lower end of the concentrations that we see here, despite the fact that we know that in some waters the metal is going to be much less toxic. So what we really want to do is to be able to explain and predict why we see the variations that we see in this chart. And that is what the Biotic Ligand model tries to do. So this chart attempts to explain in simple terms how the Biotic Ligand model works. The key assumption is that for a metal to be toxic, it has to interact with the organism by binding to a specific receptor site on its tissues, and this is the biotic ligand. And the effects of water chemistry happen through two mechanisms. Firstly, you have ligands such as carbonate or natural organic matter in the water column, and they actually compete with the biotic ligand to take up the metal ions. Therefore, for example, if one has a water with a high natural organic matter concentration, in comparison with a water with a low organic matter concentration, less metal would bind to the biotic ligand and you'd see less toxic effect. The other effect of the water chemistry comes about because certain cations in the solution, such as the proton or magnesium or calcium, can also bind to the biotic ligand, and therefore they compete with the metal to be taken up. So therefore, in a water with a high calcium concentration, compared to a water with a low calcium concentration, you would see lower metal binding to the biotic ligand and therefore lower metal toxicity in the high calcium water. So the biotic ligand model explains these influences in a quantitative manner, and by parameterizing it using the data that we saw in the previous chart, we can make a prediction of how the water chemistry is going to affect the metal toxicity. And this chart shows us what a BLM fitting results in. These data are the same toxicity data as we saw before for copper, but now we are plotting them against what the parameterized BLM predicts the toxicity would be. As you can see, the model makes a very good prediction of how the toxicity ought to vary across the different water chemistries. So this gives us great confidence in the Biotic Ligand model as a tool that we can use in order to predict how metal chemistry varies across waters, and we can take this forward, and it has been taken forward, into several risk assessments for metals such as copper and zinc. Now, when we come to radionuclides, many radionuclides are metallic in nature, and therefore they are amenable to having a BLM developed and applied for them, so that we can understand and predict how water chemistry affects their toxicity. The greatest challenge, really, in applying a BLM is in designing the quite considerable amount of experimental work that needs to be done in order to generate suitable data for parameterizing the model. And this is what we are currently doing and are well advanced with in the STAR project for uranium. So that concludes my short presentation. Thank you very much for listening.